In today's lesson, we're looking at slope fields. Now, there's quite a bit to get down here, so feel free to just watch and listen, and then perhaps pause the video to get the notes down in your book. A slope field is just a visual impression, it's a picture, right, of possible solution curves for a first-order differential equation that is written with y dash as the subject. So, in other words, one that's written as y dash equals something. Now, this is new notation, g of x dash y, x comma y, that just means some expression that's got x's and y's in it, where either of those could be zero and could be, in effect, missing. Now, at each point, P, on a solution curve, the gradient of the tangent to the curve, and the curve itself, in fact, will be given by some formula. Now, that's just a fancy way of saying we can look at what the gradient is anywhere on a potential solution curve. And we can potentially graph all of the possible gradients in a bunch of different places. Now, we're not going to graph it in every single place it could occur, but we're going to use a grid on a Cartesian plane just to graph a bunch of different line elements. So we can draw a line element. Now, a line element is just a short line of a fixed length. And we can draw it at many points, displaying the same gradient that a solution curve would have at that point. This will make a lot more sense on our first example. Now, you can calculate the gradients for each point in a table if required. I've written if required because sometimes you've got tricky gradients to work out and it makes sense to work them all out first and write them down, then draw them. Other times you'll find that a table isn't really required because there's some pattern that makes it quite straightforward to just do it on the fly. Now, we want to center each line element on the appropriate point. So on basic points of the Cartesian plane, and you'll need your graph paper for this so that you can easily work out gradients, we'll create our line elements, and the picture that we make is called a slope field. So let's have a look at how we can make one. So let's make a slope field now for the differential equation y dash equals a half x. Now, we said it needed to be in the form y dash equals something, and that the something would be in terms of x and y. Now, this is quite a simple one. It doesn't have any y's in it. We can still create a slope field for it, and what you'll see is that the table of gradients ends up being quite simple. Now, on the page before, you will have seen that I wrote if required for creating a table of gradients, and I think you'll see in a minute why I haven't bothered making this whole table. For other examples, I would. Now, I've set the scene here for my slope field. For you, this will just be a little section of your grid book. Obviously, mine is a bit messy and I didn't even have a ruler, so I've basically just made myself some graph paper. So bear with me, it's a little bit ad hoc. Yours should look better. Now, we're creating a slope field here, so I'm considering x values from -4 to 4, because that's the size of the slope field that I'm wanting to make. And so my y values also go from 4 down to -4. So over here, this is sort of echoing that. The x values start low and go high, and the y values start high and go low, so that it's literally a picture of what the gradients will be. So as we work our way along here and say, well, it doesn't actually matter if y is 4. When x is -4, what's the gradient going to be? It's going to be half of -4, right? So it's going to be, let's do this in purple, -2. When x is -3, we've got half of -3. It's going to be -3/2. When x is -2, we've got half of that, -1. And then we're going to have half of this, half of this, half of that, half of that, half of that. We could write 1.5 or 3/2. Actually, let's write 3/2 because these are gradients. It helps us to think rise over run. And half of 4. Now, I've just considered the first row of my table. Now, for some of these, as I said, you'll want to make a whole table. But what's going to happen on the next line when I'm considering what happens when y is 3? Well, because y isn't actually in my little equation there, it actually doesn't matter what y is. So I'm going to write here, it doesn't matter what y is. Now, I'm only writing this on our first one because we're new at this. After a while, you're not going to write things like this, obviously. It doesn't matter what y is. The gradient is determined by x. So I'm not going to bother making my whole table here. I'm just going to go ahead and start making my slope field. Now, how do we do it? Well, we go to the point x equals -4, y equals 4. So that's a point, and that's up here, right? It's right there. And on that point, we want to construct a line segment, and we'll make that line segment roughly half a unit long. So if this is 1 unit, roughly half, perhaps even a tiny bit bigger than that. You'll get a feel for how big to make them so that they're not running into each other, but they're not so small that you can't see the gradient. So we need to draw a gradient of -2. Now think what -2 looks like. It's going this way, and it's got a rise of 2 and a run of 1, and it's going in that direction. So we need to basically just draw a little line that's got that angle to it. Now, if you're on graph paper, obviously you can see that going down 2 and across 1, we need a line that has that gradient. So getting your ruler, actually I do have one. Here we go. It just wasn't long enough. Oh, nearly was long enough for those lines. All right, we'll use a ruler. We want a section that has this gradient. So use some of your grid to find the right gradient and then draw a line segment. Now it only needs to be relatively short and centered around that point. So now for the point x equals -3, y equals 4, which is just going along. So we're going to make gradients all the way along here with line segments of these gradients. We want -3/2. So that means we need to center it here. Now if I go down 3 and across 2 from this box to this box, that's the gradient that I want. So I can actually make the gradient with my ruler and then draw a short section of line. Oh, that's a little bit too long. Make it the same length as the other one. The next one has to have a gradient of -1. So it's here, and -1 looks like this, down 1 box, across 1 box. So use your graph paper to line it up. Draw your line segment. Now we need -1/2. So that looks like 1 box down and 2 boxes across. So using my graph paper, even though it's handmade, I've got something like that. And then I need a gradient of 0 here. So that's going to be going, we'll use our ruler, straight across. And you can see, I think, why we don't want our line segments to be too long, because we don't want them to run into each other. But we're actually already starting to get quite a pattern here. And it's kind of fun. This is basically a visual arts activity. Now we've got a gradient of 1/2. So that's going to be over here. It needs to go 1 down, 2 across. So use your graph paper, draw your line. Oops, that's a little bit long. Okay, you'll get a feel for how long to make them. Now we need a gradient of 1. And obviously, gee, my boxes aren't very good here. That's actually a rectangle, isn't it? So your boxes should actually be square, clearly, not rectangular. This is a little on the dodgy side, but you're getting the idea of the method here. And now we want 3/2. So it's 3/2. It's going to look like that. And then a gradient of 2. 2 down, 1 across will look something like that. Now, on the next line, we're going to have the exact same numbers. And if we started filling in our graph, you can see that we'd be bored by the time we got to about here, and we'd realize, oh, hang on, there's no point going down -1, -2, -3, -4. We're going to have every single row being the same. So to fill this whole thing in, and you should make one of these now in your book, I'm going to put this exact same gradient on the next line down. So a quick way to do this now would be to fill in all of those with the same gradient, going right down the page. And then the quick way for a slope field like this would be to complete each vertical line. Now that you can see what it needs to look like, this one, they all need to be parallel to this. So we've got, this was 3/2, so I could go right down my page doing all of the line segments that are parallel to that one, and then all of them that are parallel to this one. These all have a gradient of 1, and so on. Okay, so I paused the video there so that I could go ahead and complete my slope field. I've already put in the disclaimer that my graph paper was pretty dodgy because I literally just drew up some boxes. Yours is going to look much better because you're actually using squares. Some of mine are a little bit rectangular. But you can see here that even on my pretty dodgy graph, we've got slopes here reminiscent of curves. Now, what type of curves? Well, if we integrate this thing, we'll be able to see what all of these solution curves have as their formula. So integrating this, we need to raise the power by 1, so we'll have x squared, and divide by the new power. The constant comes along for the right, so we've got 1/2, and then we've got another 2 down on our denominator there. So we've effectively got 1/4 x squared plus something. So that's just basic integration there. We can see that all of these are going to be parabolas that are just lifted up or down from each other, just vertical translations. And they are all going to be translations of a parabola that has 0, 0 as its vertex. So they've got that even symmetry. So sketching a solution curve is something that we can do with this now, so that we're basically roughing in what some of the solution curves might look like, and we've got the slope field there so that we can sort of imagine what the rest might look like. We're not going to draw all of them because then we'd be filling in the entire plane. So I've written here, when we are sketching a solution curve, we thread it through the slopes. So we want to sort of use these slopes to guide our thinking, but bear in mind it's not a dot to dot. So when we do a table of values and we're actually looking at points that are on a curve, this is not a table of values, this is a table of slopes. But when we have a table of values, we could make dots and we could effectively join the dots up. Here we've got slopes, but each slope is just, hey, if you're going through this point, do it at this angle. Now we might not be going through that exact point depending on where we've started. So where do we start? Well, we know that solution curves generally don't cross each other because here we can see they're vertical translations of one another. And if we want to know which one to draw first, use the initial condition if there is one. So for something like this, saying, hey, what's the most basic version of one of these? Perhaps going through x equals 0. So in other words, going through the origin. So if I want to draw a solution curve that goes through the origin, I'll say to myself, as I'm going out this way, I need to bear in mind that as I go through this vertical line, I need to pass through it with a slope that's like this. So I can head out this way. I'm bearing in mind that as I get through here, I need to be going with a slope that's a bit steeper. Whoops, a little bit sketchy here, but we are sketching, remember, it's an art activity. As I come through here, I need to be getting steeper and then steeper. Now I'm threading my way through the curves, and it's not exactly perfect. I might have got a bit steep there towards the end, got a bit carried away. So it's going something like that. I'm going out the other side. I'm threading my way through the curves, and I have something that looks sort of like that. So it's a parabola. Its formula would be y equals a quarter x squared, this one, because the initial condition, sorry, I shouldn't have written really x equals 0. I'm letting c equal 0, aren't I? But it's going through the origin, 0, 0. And now if I want to sketch some more, just pick a point. How about we sketch one that goes through the point 0, 2. It's going to go up sort of roughly like this. Now you don't have to make them perfect because, as we said, they're sketches. They're giving us an idea of what the solution curves might look like. Going out something like that. So sketching a solution curve, we're threading it through the slope field, and now the rest of the slopes give us an idea of what all of the other solution curves look like. And it's kind of, I don't know, I think it's quite a pretty pattern. They're kind of fun to draw, a little bit tedious and time consuming, but we're effectively just solving this differential equation by drawing all of the solution curves there could be. And a couple of other points to get down. If the gradient is undefined, that's pretty clear. I think draw a vertical line segment. And when sketching your solution curves, look out for those points where the gradient is equal to 0, because obviously these are going to be the location of your turning points.